This is Module 14, Lesson 2. This time we're going to look at more heat changes, but we're going to look at something called enthalpy. So when heat is being studied in chemistry, the most common way for it to be done is through something called calorimetry. And so calorimetry uses a calorimeter in order to measure the heat that goes into or out of something. So for example, a calorimeter is kind of like a cup. It's like an insulated device like a thermos. So you might fill a calorimeter full of water like this and then put a metal sample down inside of the metal or down inside of the water and then put a thermometer here inside of the calorimeter, my ugly thermometer, and measure what happens to the water. The reason that we do this is because you really can't stick a thermometer inside of the piece of metal, but we know that if we put a piece of hot metal inside of some water, the metal is going to heat the water up and we can measure the temperature change of the water. That's easy to do. So there are different types of calorimeters. One of the most commonly used ones in chemistry classes is just simply a styrofoam cup. So here's a picture of what that would look like if you had the styrofoam cup. You could put a thermometer through some sort of like a lid on the cup or a stopper. Lots of times you'll put one cup inside of the other because it insulates it a little bit better with air. And then you can have it full of water and whatever it is that you want to record inside of it, either a chemical reaction or a piece of metal. The other type of calorimeter that's pretty common is called a bomb calorimeter. This is commonly used to figure out how much energy is in food. What they do is put the sample of food in a cup, and it's a highly oxygenated atmosphere. There's some ignition wires up top. What that does is ignites whatever's in here, let's say some Cheerios maybe. When you burn those, what they do then is they surround this little container with water. And again, the heat that's given off by the Cheerios or the burning food heats up the water. You can measure the temperature change of the water. The whole idea with these is the idea of this. We talked before about the system and the surroundings. And it's kind of the idea that however much heat this food gives off, the water has to absorb. However much heat this reaction gives off, because that's what it's indicating is in the cup, then the water must absorb, or vice versa. And it leads us to this idea of enthalpy. Enthalpy is another way of saying heat. It's the heat content of a system. And so what we're going to be looking at for us, we're going to consider delta H to pretty much be the same thing as Q, and that could also equal a capital Q. I use all three of those interchangeably. It's this idea right here that the Q of the surroundings is equal to the negative Q of the system, or vice versa. In other words, if the system gained heat, then the system, or if the surroundings gained heat, then the system lost it. If the surroundings lost heat, then the system gained it. If the surroundings was negative 20 joules, then that means that the system had to be positive 20 joules. They have to be the opposites of each other. And that's exactly what we're going to do in this first set of problems today that's on your note sheet and your practice sheet, is we're going to work some of these problems with the idea of heat loss and heat gained. So here's our first one. We have when 80 grams of a certain metal at 90 degrees Celsius. So like from our last problems, this is a mass and this is a temperature. When it was mixed with 100 grams of water, like, oh no, now we have 2 M's. This is different from our last set of problems. And that water is at 30 degrees Celsius. So there's a temperature of the water and a temperature of the metal. The final temperature of the mixture was this. So we have a lot of T's and M's, and it's asking us for a specific heat of the metal. So here's how we're going to do this. The idea is, if we read it for a second, the metal starts out at 90 degrees and it's mixed with some colder water. So the metal is hotter than the water. So the metal is going to be negative. It's going to lose heat. And then I'm going to do the Q of the water. Whatever the metal lost, the water has to gain. And we can tell right here that what this means, that the equilibrium temperature of the mixture was 36, is that the metal came to be 36 degrees and the water came to be 36 degrees. They both ended up at that same temperature. Now, if you mess this up and you don't put the negative with the metal, honestly, it doesn't matter. As long as you make one side of this thing negative, you'll be good to go. So what we're going to do is we're going to substitute for this what Q is. Q is MC delta T. Well, I have this on each side, so let's do everything for the metal on the left side. That's going to be the negative. We'll have negative 80 grams. The specific heat of the metal, that's what we're finding. The change in temperature of the metal. Remember that delta T is equal to T final minus T initial. Didn't mean to skip slides there. Apparently when I touch the screen, it does that. I don't want to do that either. I'm doing all kinds of things I don't mean to do. Excuse me. So what does our metal do? The final temperature of the metal is the equilibrium temperature. That's 36. The initial temperature of the metal is 90 degrees. Okay, what about the mass of the water? It's 100 grams of water. We're assuming that it's liquid water, so if you use your reference table, the specific heat of liquid water is 4.18. And then what happens to the water? Well, the water ends up at 36 degrees as well, and it's going to start out at 30. So now, you have quite a bit of math here to do. You can pause the video. That'd be my suggestion, would be pause the video and see if you could solve for C, because if you don't come up with the same answer that I came up with, then something is going wrong in the calculator. Keep in mind that this is a negative. So you're going to end up with a negative temperature change here, but when you do the negative of a negative, it'll become positive. You should end up with a positive answer. I got positive 0.58055 repeating forever. Now, let's talk Sig Figs, the thing that you don't like to talk about, I'm sure. This has 3. Now, our temperature change, keep in mind, remember with temperature changes, or remember with these, it's about the decimal. All of these have 1 decimal space, which means that I get to keep all 3 of those. That has 3 Sig Figs. Now, when I do the 36.0 minus 30.0, that's going to come down to 6.0. This has 2 Sig Figs. So my final answer is actually going to come down to 2 Sig Figs because of this. So that means I get to keep the 5 and the 8. So that'll be 0.58. Now what do I put in terms of units? Well, remember that your specific heat is usually in like joules per gram degree Celsius or calories per gram degree Celsius. The only thing that you have to go by is this one. It was in joules per gram degree Celsius. So that means this one's going to be in joules per gram degree Celsius because, I mean, it has to be in the same thing. All right, so there's our answer for our first one. If I lost you at some point with this, you can watch the next 2 examples that are going to occur, and you can see if those make any more sense to you. And if they still don't, then my suggestion would be go ahead and send me a message, reference this particular problem, and say something like, I don't understand how you put the negative in front of the 80, or I didn't get 0.58, I can't get that, help me, what am I doing? Like something along those lines, but reach out earlier rather than later. Now here's our next problem. I tried to choose a variety of problems, and quite a few of the problems that I chose are situations like this. Commonly what happens with these, it's like the styrofoam cup we saw earlier. Lots of times we'll want to measure a chemical reaction. And what happens is we'll put something like this, 75 milliliters of water with this much hydrochloric acid at 25 degrees Celsius. So what we're doing is we're putting hydrochloric acid, that's 25 degrees Celsius, and we're putting 75 milliliters of it in the beaker. So it fills it up to here, to the 75 milliliter mark. But we're also putting 75 milliliters of NaOH at 25 degrees Celsius. So we're putting NaOH, that's also at 25 degrees Celsius, 75 mils of it in the beaker. So that's going to bring it up to here. Well, if you add 75 to 75, that brings it up to the 150 milliliter mark. So this is our total solution that's going on in here. We had HCl to start with, and then NaOH. Now, here's what I know about this at this point. Both of these were at 25 degrees Celsius going in, which means that they're going to stay at 25 degrees Celsius when we put them together. So what do I do with this mole stuff? I just ignore it. It doesn't matter. Moles is going to have nothing to do with this. It's kind of distractor information, so just forget that it's there. But from way back in maybe module 1, we learned that 1 milliliter was the same as a cubic centimeter. That's going to come into play with some of these problems. And the other thing that we learned that I think we've used before, if not, then I'll teach it now, is that 1 milliliter of water has the mass of 1 gram, or 1 gram per 1 milliliter, because that's the density of water. I can't use milliliters in my problems. In my problem for Q is equal to mc delta T, I need mass. I've got the C of this because if it's in water, then we know the specific heat of water. And it looks like it's given us 2 different temperatures. What I'm lacking is the mass. It's wanting to know how much heat, so that's Q. So what do? Well, I know that if I have 150 milliliters, that is the same thing as 150 grams. So I'm going to use that knowledge up here. Since it's a water-based solution, we're just assuming that that's the mass of it. What about specific heat? I don't have a specific heat for sodium hydroxide or for hydrochloric acid. So what we're going to do is we're going to use the specific heat of water. And then for temperature change, this whole thing started out at 25 degrees Celsius. They both did. But when we mix them together, they rose to 35. So the final temperature is 35 minus the initial temperature of 25. This one is not going to be set to anything else. But you will have some of these problems like this where you're mixing for a reaction, and the whole key here is knowing to turn the milliliters into grams. So what I do now, I just simply do math. What I get in my calculator is 6,270. So what do we do about Sig Figs? I look at this. This has 4 Sig Figs. And then if we work with our addition and subtraction, 35 minus 25 is 10. But both of these were good to 1 decimal place, or not to 1 decimal place, but to the ones place. So is this one. This has 2 Sig Figs. So I'm going to give 2 Sig Figs. That's going to make this 6,300. And if this was in joules per gram degree Celsius, then that is 6,300 joules. That is how much heat that's in joules. But now if you read the question, it says how much heat in kilojoules. So before you get carried away, that would be 6.3 kilojoules. Because kilo means 1,000, so you need to divide this by 1,000. Now, if I can help you with that, if I can help you with how do I convert it to kilojoules, or I don't understand any of your Sig Fig stuff with this stupid addition and subtraction thing, then let me know. It's commonly the cause of frustration, and it'll be the cause of you missing points on the quiz or the test, so make sure to ask if you're not understanding it. Now for my last example. All right, what about this one? You have an 8-gram piece of aluminum that's heated and placed into water at 30 degrees Celsius. So what we should know is going to happen is that we have this container of water that's at 30 degrees Celsius, and we're putting a little cube of aluminum in here, and this little cube of aluminum is at 100 degrees Celsius. So what's going to happen? Well, the heat is going to move out of the aluminum and into our water. So that's leaving us with doing this. The negative Q of the aluminum is equal to the Q of the water. And again, like I said, if you put the negative in the wrong place, it's okay. Just move it to the other side. You'll still come out the same. If you don't believe me, try it sometime. Trust me on it. So we're going to do the negative mc delta T of the aluminum is equal to the negative mc delta T of the water. That's going to be negative 8.0. What about the specific heat of aluminum? Use your reference table. It's the first specific heat for the non-water stuff. It's 0.897. Some century I'll have this thing dialed in completely. Now, the change in temperature. We're looking for the final temperature of the aluminum. Well, we should know that in these problems, the final temperature of the aluminum will equal the final temperature of the water. That means I don't know either one of these because they come to an equilibrium. I don't know it. So keep in mind that delta T is TF minus TI. I'm going to plug in what I do know. I don't know TF. I know that the initial temperature of the aluminum was 100. And I touched the screen too fast. I was wanting. Okay, the mass of the water is 250 grams. The specific heat of our water, again, we assume liquid water, that would make the most sense, is 4.18. I don't know the temperature final of the water because we just said we don't know it for either one of them. But I do know that the initial temperature of the water was 30. Yikes, this looks ugly. It looks ugly, but I really don't think it's all that bad. Keep in mind, like, this becomes an algebra problem now. So what we're going to have to do is we're going to have to multiply these two together. And I'm probably going to do this in more steps than I would do for myself, and probably more steps than many of you would do. So if we do this, 8 times 0.897, and it's a negative, is going to be negative 7.176. Well, all I'm doing is just simplifying this sum, okay? When I touch it too quick, it sends me to the next slide. And now if I wanted to tap it to make it go to the next slide, it would never happen, right? Okay, so simplifying this side, 250 times 4.18 is 1,045. And that's going to be times this. Okay, so what I've done is just made it a little bit nicer looking. What do we do in algebra class? We're going to have to distribute this negative 7.176 through the parentheses, because it's going to be this times TF times this times negative 100. So that's exactly what I'm going to do. Well, this number times TF is just going to stay that. When I have negative 7 times negative 100, that becomes positive 717.6. Now on this side, it's positive 1,045 TF minus 31,350, because I did this number times 30. And since this one's positive, this stays negative. Well, now what do? You hateful teacher, you, for making me do this? Well, you combine like terms. My suggestion would be take the negatives to the other side. Like, remember, if this is negative, then I need to add it to both sides. And I need to add 31,350 to both sides. So when I do that, somehow I didn't finish it on my own paper. I was looking at it. So when I add 31,350 to 7, that didn't even type it in right, 31,350 plus 717.6. I get 32,067.6. Now, bless it, every time I do the equal sign, I'm doing it too fast. I don't know. Then I've got 1,045 plus 7.176. That is 1,052.176 TF. Remember, the TFs go together there. Now, what do? Now, I need every equal sign, y'all. You think I would figure this out at some point. Hopefully you're laughing at me instead of ready to pull your hair out. 32,067.6 divided by 1,052.176 comes out to be 30.477 ... Now, of course, when I do that, it stays there. I don't understand it. So, does that seem reasonable? Yeah, I mean, first of all, did the temperature of the water increase? Yes, it did. It went up a little bit. This is not a lot of aluminum. This is a pretty fair amount of water compared to aluminum. So yes, that seems reasonable. What about the ugly Sig Figs? Well, you're going to go, easiest thing I know to take at this point is, like, I don't really care about Sig Figs on this one. That's a lot to think of. Is just look back up here at your problem. This has 2, so we're going to call it 2. So the final temperature would be 30 decimal. And I know that seems weird since, you know, it started out at 30. You could give it one more decimal if you want to, which would be 30.4. Actually, 30.5. I stand corrected since there's a 7 beside of it. You know, it's a lot to think of with the Sig Figs. So when you go to this much math, I'll be honest, like, I really don't care. So just match it up with whatever you have up here. If this has 1 decimal place, then give the final temperature 1 decimal place. That works for me. All right. You do have some of these on your practice problems. Just do the best that you can. Now, at this point in your notes, if you look at those, you will eventually have a gray bar telling you to return to the video. I do have one more type of sample problem, and you can either continue on to that or you can stop and try these. Our last type of problem has to do with thermochemical equations. Now, a thermochemical equation is simply a chemical equation that has this enthalpy stuff written into it. It oftentimes has heat of reaction, and sometimes you'll see it written with a little degree sign up there, and then it'll be written that way down here. I don't care if you put it there or not. I didn't. But basically, what this comes down to is when you see the delta H, when you see the enthalpy right here, if it's a negative, then what that means is that it gets written in the products because it is exothermic. Remember that the products are coming out of the chemical equation. So what this means is that when you have CaO and H2O, they produce 65.2 kilojoules. And you'll sometimes see these as kilojoules per mole, and that's fine as well. But what that means is that for every mole of the substance that was in here, this produces 65.2 kilojoules. So know that if it's negative, it should go on the product side. And likewise, if it's positive, like this one, it'll go on the reactant side. If it's positive, that means it's endothermic. So for this means basically how you can interpret this then is like a stoichiometry problem. 4 moles of NO would require 905.4 kilojoules. 6 moles of water would require 905.4 kilojoules. If 4 moles of NH3 were produced, it would require 905.4 kilojoules. 5 moles of O2 produced would require this many kilojoules. Up here, it's all 1 mole because the coefficients that you have in front of all of these are an understood 1. Now it's proper, it's balanced that way. 1 mole of calcium oxide makes 65.2 kilojoules. 1 mole of water for this one makes this many kilojoules. So, you're going to use the equation to solve these problems. So the amount of heat released or absorbed, it depends exactly on the number of moles of the reactants or the products that are in the problem. What I have up here too is heat of combustion. And what that is just the heat of what's burned. You'll see it written the same way. Like if it is a combustion reaction, you will be given the same number. It's really specific to a combustion reaction. That's the only difference with it. So what we're going to do is we're going to do some of these problems. So you have these in your packet. There's only 2 of these. It asks you to calculate the amount of heat evolved. That means released or given off. If you have 15 grams of this forming from the reaction. So here's what I do know. I know that this is negative, which means it's going to go on this right-hand side. I didn't leave much space in there. And I know that there's this much given off per mole of this. So what I'm going to have to do is I'm going to have to put down the grams, and you are going to be using your old mole problem knowledge to convert this to moles of CaOH2. So what are we going to have to do to come up with this? We're going to have to add the numbers off of the periodic table. Calcium has a mass of 40.1, so you've got 40.1 for the calcium plus 2 oxygens, which is 32, plus 2 more for the hydrogen. So this has a mass of 74.1 grams per mole. What's my next step? I know that this is per mole, and this should be kilojoules. Somehow I left that off of there. In the PowerPoint, it's proper on your paper. So you could put the per mole or you could just know it. So if there's 1 mole, there's 1 mole right here in the equation is going to release negative 65.2 kilojoules. Moles cancels, grams cancels. It's time to do math. So we've got 15 times 65.2, and then that will be divided by 74. So we get 13.198 ... It keeps going on. So what about Sig Figs? You simply go back to what you started with like we did in the mole problems. That has 3, so I can keep 3. That'll be 13.2 kilojoules Now, about this negative thing, you could put negative 13.2 kilojoules, or with words, you could put 13.2 kilojoules released. Doesn't matter, yes? It's like saying, I lost $20. Well, if you wrote that down, you would just simply write, I have minus 20. You wouldn't say, I lost minus 20. It's a double negative. That would turn it into a positive. So you can do one or the other, but not both. Now, here's your other example. What about this one? This one also happens to have heat being released, which breaks it up right here. It means it goes right here. You would put it on this side, plus 184.6 kilojoules. We never write it as a minus in an equation. So how much heat is generated if 5.67 moles of product are formed? Well, this is the product. It's that many moles of hydrochloric acid. Well, now here's the nice thing about this one. It starts at moles. So I know for this equation that there are 2 moles of HCl for every 184.6 kilojoules. I put the 2 this time because I'm using the coefficient from the problem. Now on this one, I don't have to do quite as much work. And as you can hear, I'm punching it into my calculator. I get 523.341. What about Sig Figs? Go back to your original. I can have 3. That's 523 kilojoules. Now again, this was a negative. It's a negative right here. So I can either put negative 523 kilojoules, or I can put 523 kilojoules released, generated, emitted, evolved, however you want to say it. One of those 2 answers will be sufficient. If it's a positive value, then you just simply give the positive number, and you're welcome to say absorbed if you would like to. So at this point, it's time for you to either do all of them or finish off the rest of these thermochemical calculations, because that's what you have left. Let me know if you have questions during office hours or send me a message beforehand.